Hi, this is Sudeep, and I welcome you back to this wonderful journey of learning structure analysis with STAAD.Pro. We are in the third part in this series today, where we are modeling loads in STAAD.Pro. In the last two episodes, we have seen how we can model the concentrated loads, both which are inclined and which are oriented along the global axis within STAAD.Pro. Today, we will discuss about the uniformly distributed loads. But before we go forward, please do take a moment to hit the subscribe button if you are new to this channel and join us in this wonderful journey of learning structure analysis with STAAD.Pro. Now, as I've said before, we will discuss about the uniformly distributed load today. Now, what is this uniformly distributed load? A uniformly distributed load is a load which is applied uniformly throughout the member length. Now let us see an example of this, and we can consider the self-weight of a member or a beam as an example of a uniformly distributed load. Now let us consider this member or the beam that you see on the screen, and let us consider that a homogeneous material makes this beam, the weight density of which is 25 kilonewton per meter cube. Let us consider that this beam is made up of a rectangular cross section, 250 millimeter wide and 400 millimeter deep. Now, with these two inputs, we can calculate the self-weight of the beam per unit length as the product of the weight density and its cross-sectional dimensions, and we get the value of self-weight as 2.5 kilonewtons per meter. Now, this means that the weight of the beam per meter length of it is 2.5 kilonewtons. Now, this is an example of a uniformly distributed load. As you may have noticed, the unit of a uniformly distributed load will be given in force by length or force per unit length. Now, we know that the self-weight is an intrinsic property of the beam. However, we can consider this to be an externally applied load on the beam if we consider the beam itself to be weightless. Now, we will consider this case, which we will model in STAAD.Pro. This is the model of a simply supported beam pinned at one end and having a roller support on the other and having a 5-meter span and is subjected to a uniformly distributed load of 5 kilonewtons per meter. Now, another input that is necessary for defining this load will be the direction of that load. And we see that this load is being applied along the global y direction. To speak exclusively or rather clearly, we can say that this load has been applied in the negative direction of the global y-axis. Now let us see how we can define this load in STAAD.Pro. So this is the model that we will be working on, which is the model of a simply supported beam having a pin support at one end and a roller support on the other, which has been defined with a fixed butt support. Now, if you want to know more about fixed butt support, you can visit the session by clicking on the link that is appearing on the top right of this screen right now. Now, let us go to the utilities and quickly check if the span of the beam is okay. We wanted our beam to be a 5-meter in span, so it is 5 meters. So now we can switch off the dimension display. Now let us go to the load case details and click on the add button. We define a primary load case, and yeah, the title can be load case 1, or we can change it to say UDL of 5 kilonewtons per meter, and click on the add button. Now we select the item, the load case item on the screen, and you can see that the load items will be displayed here. Now to define the uniformly distributed load, you need to click on the member load option. Now you can see that there are a lot of varieties of the member load option. We need to click on the uniform force to define the member load option. Now, firstly, we have to be concerned about the direction. The direction has been specified as GY, which is the vertical direction, and we know that the load has been defined in the negative direction of the global y-axis. So we'll define our load as minus 5 kilonewtons per meter. Once we have done this, we click on the add button and we can see that this item has been added in the load and definitions box. So we click on the close button and we now assign this load to this particular beam. You are already aware of the assignment method, so I won't repeat that. So we can see that the load of 5 kilonewton per meter has been assigned on the length of the beam. Now we want to check what is the command instruction for defining a member load. So we go into the text editor. You'll be prompted to save the file. So click on the save button. So now we are in the text editor and we can see that the load case has been defined. Load case 1 has been defined as member load. So if we go down and make this bigger, we can see that load case number 1 has been defined, the title of which is UDL of 5 kilonewton per meter. We have the member load specification, and under the member load we have this specification of the load, which is 1, which is the member number. So the member number is 1, uni, which would mean uniformly distributed load, GY, which means the global y-axis, and the load magnitude is minus 5, which means that it has been specified in the negative direction of the of the global y-axis. Now, one question would be, what is the unit of this load? Well, you remember that we had defined our loads in the units of meters and kilonewtons. So thus this load that will have a unit of 5 kilonewtons per meter. Now, one thing that um, uh, we had discussed in the past is about how to define the unit system. And if you want to see that discussion, you can click on the screen or on the link that is appearing on your screen right now that will take you to the session where we had discussed this. Now, there can be cases where the uniformly distributed load has not been applied on the full length of the beam and has been applied only on the partial length. So let us consider this example of the same beam that we had just discussed, but in this case, we are considering a uniformly distributed load of 5 kilonewtons per meter applied only on the partial length of the beam instead of the full length. Now, to specify such a beam, STAAD would need to know the distance of the start of the uniformly distributed load from the start node of the beam. So let us consider that that distance is 1.5 meter. Now that is being considered as the distance d1 while you specify the uniformly distributed load. Again, the next thing that STAAD would need to know is the distance from the start node to the end of the uniformly distributed load of 5 kilonewtons per meter. Let us consider in this case that distance is 3 meter, which would be considered as D2 while you define the uniformly distributed load in STAAD.Pro. So D1 as 1.5 and D2 as 3 meters. The uniformly distributed load, the magnitude is 5 kilonewtons per meter. Now let us go into the STAAD.Pro environment and see how we can define this. So in the same beam, what we'll do is we'll define another load case. The first load case is where we have the uniformly distributed load of 5 kilonewton per meter that has been applied on the full length of the beam. Now let us define another load case where we would apply the partial uniformly distributed load. So let us say the title is partial UDL of 5 kilo, sorry, it's partial UDL of 5 kilonewtons per meter, and we add the load case and now define the load item. Again, we go to the member load and click on the uniform force. We define the direction as GY. The magnitude would be -5. Now we would define D1 as 1.5 meter, as I had just explained, and D2 as 3 meters, and we would add that to the load case as an item of the load case number 2. Now there is another parameter called D3 which you may notice, but this is something that we would consider later on. Now we close this and define this load item on the beam, or assign this load item on the beam, and we can see that the uniformly distributed load now has been applied partially on the particular beam. Now let us go into the text editor and see how this has been defined in the text editor. So now in the load case number 2, we can see that we have the member load, but as in the first load case we only had the magnitude of the load. In this case, in addition to the magnitude of the load, we also have two additional terms which are defined as D1 and D2 in the graphical user interface. The first number, 1.5, is nothing but the distance of the start of the uniformly distributed load from the start node of the beam, and this number 3 is the distance of the end of the uniformly distributed load from the start node of the beam. Now, I hope we have understood this. Now, let us consider the application of the uniformly distributed load of 5 kilonewtons per meter as shown in this figure. Now, as we can see, this uniformly distributed load is applied transversely on a member that is not aligned along any of the global axis system, or that particular member is inclined to both global X and global Y. This would mean that there is no way that we can define this uniformly distributed load of 5 kilonewtons per meter along the global axis direction. Yes, we can definitely break it into components, two equivalent, or rather two uniformly distributed loads, one along the x direction and one along the y direction, such that the resultant equivalent uniformly distributed load is 5 kilonewtons per meter. We can do that, but that would mean that the user would need to do a lot of manual calculation. However, we can solve this problem like this. If we see the local axis system of this inclined member, which is the default beta 0 orientation of the member, we can see that we can define the uniformly distributed load along the local y-axis. Now, if you are not sure how the beta 0 orientation of the local x-axis of this member is like this, you can always refer to the session where we had discussed this in details by clicking on the link that is appearing on the screen right now. Now, once we have explained this, as you now understand that we can apply this uniformly distributed load by defining it along the local y-axis. And since this load is acting in the negative direction of the local y-axis, we will define that load as minus 5 kilonewtons per meter along the local y-axis. Now let us see how we can define that in STAAD.Pro. Now we see that the member or the frame that we had just seen has been modeled in STAAD.Pro. So let us model the uniformly distributed load of 5 kilonewtons per meter on this inclined member. So what we do is we click on the load case details, click on add, click on the load cases detail, click on the add button, define a primary load case. Let us say we want to describe UDL on incline member. So this is the name or the title of this load case. And we click on the add button, click on the title and select the member orientation. Of course, let us say that the uniformly distributed load is minus 5 kilonewtons per meter. Now, before defining that along the local y-axis, let us see what would happen if we define this load along the global y-axis on the inclined member. So let us click on add, and we can just drag this down, click on this member, and use the cursor to assign option and assign it to this particular inclined member, and we can see that this load is not as we had intended. So what we do is we would like to modify this load and define that along the local axis system. So we double click on this member again, retain the magnitude of the load, and instead of global Y, select the local Y option and click on modify, and you can see that the load has now been modified and the uniformly distributed load of 5 kilonewtons per meter is applied on the inclined member exactly as we had wanted. You can switch on the you can switch on the member orientation by clicking on the beam orientation, and you can see that we had just switch off the load view for a moment, and you can see that we had defined the local y-axis is the positive direction of the local y-axis is opposite to the direction of the applied uniformly distributed load. So, and that is why we now have the uniformly distributed load applied exactly as we had wanted. So with this, we have completed the modeling of the loads as well. In the next session, we will look into the analysis command of STAAD.Pro and what that means. If you have liked the session today, please to hit the like button and help me to reach out to students who are looking out for a similar content. I hope to see you in the next session. Till then, bye bye.